This video is to help you understand section 3.1.1 using the multiplicative identity. In this lesson, you're going to analyze a powerful tool for finding equivalent fractions. This way of thinking about equivalence can be applied to many different situations. You'll see how it can be used to solve problems and investigate new applications. So, starting with 3.1, Ms. Vasquez has a reputation for telling math jokes. She started class today with this one. Ron was picking up his pizza at the takeout window. The clerk asked him, "Do you want your pizza cut into 8 slices or 12? "You better cut it into 8 slices, Ron said. I'm not hungry enough to eat 12. Some students thought the joke was funny. Do you? And then what is the fraction concept that makes the joke work? So, of course, the idea here is that the whole pizza is the same size, no matter how many pieces you cut it into. For 3.2, Frankie's mom's on a diet where she's concentrating on portion control. She makes all her meals once a week and puts them in the freezer already packaged into single meal servings. Her doctor told her to try cutting her regular servings into halves, thirds, or even fourths to reduce the amount of food that she eats. Her mother made a big pan of lasagna last night. She cut the lasagna into fourths and ate one. Then she put away the 3 pieces of leftover lasagna by cutting them each in half and repackaging the results. This process fascinates Frankie. How can you make something smaller and still end up with more, she asked. So they want you to write a fraction representing how much lasagna was left after she ate her dinner. Write another fraction representing how much lasagna was left after it was repackaged. Does she really have more lasagna after repackaging? So if we look at the fact that initially she had this whole pan of lasagna, all right, and she ended up cutting into fourths and eating one. So she's left with 3/4 of the pan. Okay, so 3/4 of the pan right now is left in terms of lasagna. Okay, so I'll make it kind of orangey red and yellow here to make it look like lasagna for us. Here's our noodles, there's our sauce, best I can do. All right, now what's happening is she's cutting it into half. So each of these pieces, all right, has been cut into halves, which is what I did here. Okay, I cut them into half. So there's 3 pieces left out of the 4, and we've cut each of those pieces into half. So the fraction that represents how much was left is 3/4. All right, and then once she's cut those slices into, halves, she now has 6/8 left. And of course, the idea here is that that is still the same amount of lasagna. She may have twice as many pieces, but they're each half as big. Okay, 3/4 is what we say is equivalent to 6/8. They are equal in value. Frankie was thinking about her mother's portion control, cutting up the lasagna, when she noticed a very useful connection. She recognized that any fraction in which the numerator and denominator are the same is equivalent to 1. In addition, multiplying a number by 1 leaves the number unchanged. Wow, she said, I can use this idea to find a whole bunch of equivalent fractions. She showed her team the work that's shown here. Look, she said, it's the same as using a giant 1. So what they're showing you is if you took the fraction 3/5 and you multiply by 1, it should still have the same value. And that 1, of course, is any fraction where the numerator and denominator are the same as each other. So 3/5 times 1 remains unchanged. 3/5 times 2/2 gets what we call an equivalent fraction, equal in value, but still the same value. So equal in value, looks different, same value. Right? So hopefully that should make sense. If you multiply something by 1, it does keep that value equivalent, equal in value. But again, the fraction looks different, so we call that an equivalent fraction, and that means it looks different, but is the same. Then they want you to find 2 other fractions or ratios that are equivalent to 3/5. So again, you don't need to use an actual 1. If you want to just use a rectangle to represent 1, that's fine. But the idea is that you can take any fraction, numerator being the same as denominator, equal to 1, multiply it by your original, and you're going to get an equivalent one. So in this previous problem, they used 2/2. We could go with 3/3, because 3/3, of course, is equivalent to 1. And then we would create the equivalent fraction. 3 times 3 is 9. 5 times 3 is 15. So we'd call 9/15 an equivalent fraction. Equal in value, looks different. We could go with 4/4 for our giant 1. We could go with 10/10. Any number divided by itself, any number with the numerator and denominator the same, is going to equal to 1, pardon me. So again, you could go with whatever you want here. I'm just going to go with 10/10. That's a nice easy one to work with because, of course, multiplying the number by 10 just means moving the decimal point one place, in this case adding a 0. So 30/50 is also equivalent to 3/5. All right. Then they said we call that, in a formal sense, the multiplicative identity. Why do we think we call that the multiplicative identity? And the idea is that you're multiplying, okay? You're multiplying, and specifically you're multiplying by the value of 1. And what's happening is the identity of the number is staying the same. So the reasoning for why we call that the multiplicative identity is that we tend to term math things very logically. And so we're multiplying, we're maintaining the identity, so we call that process, we call that, that property, so to speak, the multiplicative identity property. And then they want you to use the giant 1 to find some fractions that are equivalent to 9/8. So again, you can use any numerator over denominator. Of course, you wouldn't use 1/1 because you're not going to change what the number looks like. We want it to look different but be equal in value. So you could go with 2/2 here. Now, because this original fraction was improper, your equivalent fraction will also be improper, and that's okay. Normally, we would change improper fractions to mixed numbers, but in this case, they're starting us with an improper fraction. They want us to find an equivalent fraction to that. You could go with 3/3. Again, 9 times 3 is 27. 8 times 3 is 24. This would be equivalent to the first. You go with 10/10. You could go with 100/100. But you can create 4 equivalent fractions that way. And they do want you to go ahead and finish those out. For 3/5, Bertram is feeling confused. There's so many ways to write the giant 1. How do I know which one to use, he whined. How could he decide which giant 1 to use? So in this case, you were getting to choose what giant 1 you wanted to use. And you can use anything at all, any giant 1, to create that equivalent fraction. But in some cases, they're sort of, forcing that for you, meaning they're setting it up and you have to figure out what is those missing values. So for A, I put it down here. So we started with 3/4. We're multiplying by a giant 1, and we're getting a value out of 44. So what we would say to ourselves is, what did we multiply 4 by in the denominator to give us 44? And of course, we multiplied that by 11. Well, if 11 is the denominator, that means 11 also has to be the numerator. So the giant 1 would be 11/11ths in this case. And then we can find that missing value by saying, all right, 4 times 11 was 44. 3 times 11 is our new numerator of 33. Same concept here. What did we multiply 12 by to give us 60, which is 5? So 12 times 5 is 60. If 5 is the denominator of our giant 1, 5 also has to be the numerator of our giant 1. And so we know that the giant 1 is 5/5. And then 7 times 5 gives us our new numerator of 35. Now here, the only thing they did different is they put the multiplication on the right side, which is absolutely fine. So again, same concept though. We'd say to ourselves, 3 times what value gives us 18? So the numerator of the giant 1 must be 6, because 3 times 6 is 18. If the numerator is 6, that means the denominator is 6. So the giant 1 is 6/6. And then we're asking ourselves, what number here, what denominator multiplied by 6 would give us 72? And that's 12. And then it says what computations can help you find the numbers that you use in the giant 1. And of course, multiplication or division. When we say something like, what number times 4 gave us 44? Well, we're figuring out what do we multiply 4 by to give us 44? or we can think of it as 44 divided by 4 gives you 11. So multiplication or division is what you're focusing on for equivalent fractions. Then it says, use what you've discovered about finding the necessary giant ones to complete this problem, right? So this one's a little tricky because if you look closely, you see that even though it looks like the other ones, it's not quite the same. Because we're asking ourselves, what do you multiply 50 by to give you 10? Not what do you multiply 10 by to give you 50, but what do you multiply 50 by to give you 10? All right, now we all know that 50 divided by 5 is 10, but what is that multiplied by to give you 10? And the answer to that is 1/5. 50 times 1/5 is 10. All right, how do we know that? Well, dividing by 5 is the same as multiplying by 1/5. It's like dividing by 2 is the same as multiplying by 1/2. Dividing by 3 is the same as multiplying by 1/3. You can also think of it as the decimal, 0.2. 50 times 0.2 is also equal to 10. So if 1/5 is the denominator of the giant one, then 1/5 also has to be the numerator of the giant one. All right, so 50 times 1/5 is 10. 35 times 1/5 is 7. Again, multiplied by 1/5 is the same as divided by 2. So how is this one different? Well, we had a giant one being a fraction divided by a fraction. We had a fraction in the numerator and a fraction in the denominator, but we can still use that for our giant one. Again, we could also have gone with a decimal, all right? We could have made it 0.2 over 0.2. Another way to make sense of this problem is that when you multiply by 1/5, it's the same as, it's equivalent to divided by 5. Now that concept might be a little tough. Again, maybe take some time, pause the video, make sure that you're comfortable with that idea. All right, then for 3.7, it says sometimes it's useful to express a fraction in simplest terms or lowest terms. If you write a fraction in lowest terms, we're trying to use the smallest whole numbers possible to express the fraction. So for example, 60/70ths, 30/35ths, and 6/7 are all equivalent fractions, but only the fraction 6/7 is expressed in lowest terms. Simplifying a fraction is the process of rewriting it in lowest terms. So we want to think about how we can use that giant one to help us simplify fractions. So what they did for A is Tessa has written this work, and again I made it just a little bit bigger off to the side. So she had 55 over 500, and she broke 55 down to be 5 times 11, and she broke 500 down to be 5 times 100. They wanted you to see where the giant one is in there and how we then have equivalent fractions. Well, when you break the 55 into 5 times 11 and the 500 into 5 times 100, you see a giant one here, right here. Okay, 5 over 5 is a giant one. So since this is equal to 1, 1 times 11 is 11, 1 times 100 is 100, these two are the equivalent fractions. Okay, so it says, does work make sense? And hopefully it does make sense to you. All right, yes, that works. Is that expressed in lowest terms? How can you tell? Well, it is expressed in lowest terms. The way you can tell is when there's no other giant one that you can pull out of that. In other words, there's nothing that 111 will divide by other than 1. So they have been simplified as much as possible. They've been taken down to the lowest terms. 11, the only thing that'll multiply to give you 11 is 1 times 11. And 100 has lots of factors, but the only one it would have in common with 11 would be 1. When you get to the point where there's no common factors between the top and bottom, other than 1, we say it's in lowest terms or simplified. Okay. Again, that's a really important concept. You may want to go back and take some time to look at that. But the idea is that the GCF, the greatest common factor of 11 and 100, is 1. There's nothing else that they will both divide by. So C, Tessa's doing well. She decided to try another problem, and she wrote this work down. So she made 28 into 2 times 14 and 60 into 2 times 30. And again, I made it just a little bit bigger here on the side. So we know that we have the giant one here. Okay. So 1 times 14 is 14. 1 times 30 is 30. So these two fractions are equivalent. 28 60ths is equivalent to 14 30ths. Right? So they want to know, is her work correct? Yep, what she's done so far is correct. But is her fraction in lowest terms? It is not. Okay, it is not in lowest terms because there's still a common factor between 14 and 30 that's not shown, which is that, and I'll try to make room for it here, 14 and 30 both have a common factor yet of 2. So you can break 14 down into 2 times 7 and 30 down into 2 times 15. And because you can do that, you see the giant one here of 2 over 2. So it can be simplified further and simplified fully down to 7/15. So it was not in lowest terms until we found that remaining common factor between the numerator and denominator. You can do that in one step. Like back here, you could have realized that, gee, these both have a common factor of 4, and then you would get to 7/15 in one step, or you can do it in a couple steps like we did here. So the idea with D is to practice that. Practice simplifying these fractions. Okay, so I'll do a couple of them with you. Let's look at 24/36. Again, you could say to yourself, well, 24 is 2 times 12, 36 is 2 times 18, and that works fine. But if you could find the largest common factor between them, or even a larger common factor first, it means less steps. So that's part of why we focus in on greatest common factor. So we're asking ourselves, what is the biggest number these both divide by? So they both divide by 2, they both divide by 4, they both divide by 3, by 6. They have a lot of common factors. But actually, if the largest common factor is 12. Now again, don't be overly concerned if you did not realize that, okay? Because you can still get to simplest form without having to pull out the greatest common factor. It just takes you a couple steps, and I'll show you that too. So I can make this into 12 over 12 times 2 over, whoops, my mistake. What did I get for trying to talk right at the same time? 2 over 12 times 3 here. So then here's my giant one. All right. So 24 again is 12 times 2. 36 is 12 times 3. Since I have a giant one of 12 over 12, that means the equivalent fraction is 2/3. Okay, that would be considered in simplest form or lowest terms. Now, again, I want to point out to you that if you had not realized that, let's say you had started by saying, well, I can see that these both divide by 6, then you would have 6 times 4 and 6 times 6, which is fine. So you would see your giant one of 6 over 6, and you'd have your equivalent fraction of 4/6. What you'd have to, though, realize at this point is this is still not fully simplified, that they still have a common factor other than 1. And that would be a common factor of 2 over, 2 over 2, giant one of 2 over 2. So 4 is 2 times 2. 6 is 2 times 3. The giant one of 2 over 2 is right here. So then you get that equivalent fraction of 2/3. So again, you need to get to this final result, but whether you do that in one step or multiple steps is up to you. The important thing is to make sure your final answer is fully simplified. All right. And then you're going to do the same thing with the second and with the third. All right. 3.8, Tessa has a brilliant idea. Look, she exclaimed, if I find the largest number that's a factor of both numerator and denominator, I can simplify all the way in one step. So that's what we were getting at, all right? So what she did is she broke 60 down into 12 times 5, 72 down into 12 times 6, the giant one of 12 over 12. Well, 12 was the greatest common factor, so when she rewrote it this way, she got right away to the equivalent fraction of 5/6 then, which is also simplest form. Now, you might ask, well, how did she come up with this? What are they showing here? They're just showing that you could use prime factorization. You could break 60 down into 2 times 2 times 3 times 5, which is prime factorization. 72 down also through prime factorization. See that they had some commonalities here. So 2 was in both of them when they did prime factorization, another 2 was in both of them, and a 3 was in both of them. So 2 times 2 is 4, times 3 is 12. 2 times 2 again, times 3 is 12. So they're using the prime factorization to help pull out that greatest common factor. Okay. Again, they remind you that factoring a number into those prime factors is another way to help find that greatest common factor, like we talked about up here. It's not the only way. You don't have to do it that way, but it is a good technique as well. So then they want you to use that same idea to do these. All right, so the additional challenge, again, I'm going to let you try to challenge yourself with that. And same thing with 310. And we'll talk about homework in the next video.